Hello, my name is Joshua Cosgrove, and today I will be talking to you about the idea of differential privacy. I will start by discussing what privacy kind of in general is, giving some ideas of it and discussing them. Then I will get into differential privacy specifically, explain why it's so good, why it should be the standard. And then I will discuss how to actually implement differential privacy, explain where it has been implemented, and then finally I'll get into what it can't do. All of the information that I'm going to say in this video is going to be taken from The Ethical Algorithm, the Science of Socially Aware Algorithm Design by Michael Cairns and Aaron Roth. So if you want to get a more in-depth look at what I'm talking about, you should check that out. So yeah, let's get into it. So a simple and kind of naive idea of privacy is that no data may be collected from an individual that they do not consent to, right? That's not from the book. I just thought of that off the top of my head as just an idea of the first thing I think of when I think of privacy. But that doesn't really cover everything. Say, for example, if a person willingly gives their information, but then that information is misused. I would say their privacy has been violated, which this brings us to the idea of harm. Harm in the context of privacy is completely arbitrary. It is whatever the person who is giving up their data defines it to be. Harm is anything from receiving an annoying telemarketing call because you gave your phone number to some website, or being tracked down and imprisoned by the government because you said something critical to them, but then your data was gathered by some site and the government was able to track you down because of that. Both of those are just examples of harm. So, keeping that in mind, if you are harmed by having your data collected, that's a violation of your privacy. We could edit this definition to be more like, no harm may come to someone from the collection or use of their data. However, this idea has some problems which are best explained through the example given in the book. Alright, so imagine a man named Roger. He's a physician working in London in 1950 who is also a cigarette smoker. This is before the British doctor study, which provided convincing statistical proof that smoking tobacco and an increased risk for lung cancer are linked. In 1951, Richard Dahl and Austin Bradford Hill wrote to all registered physicians in the UK and asked them to participate in a survey about their physical health and smoking habits. 2/3 of the doctors participated. By 1956, Dahl and Hill had published strong evidence linking smoking to lung cancer. So, now, anyone following this work and who knows Roger would now increase their estimate of Roger's risk of lung cancer simply because they know that both Roger is a smoker and they know a new relevant fact about the world, that smokers are at an increased risk for lung cancer. This can lead to real harm for Roger. For example, in the United States, it could cause him to pay higher insurance premiums, which is a very real downside and harm. So what does this mean for our definition? Harm did come to Roger. People may now treat his smoking with more stigma, and if he lived in the US, his insurance rate would go up. But was his privacy violated? If you argue that it was, that would essentially make it impossible to perform any study really of any kind without fear of violating someone's privacy. However, I would argue that his privacy was not violated in this case. One, he gave his full consent and the data was used exactly how he expected it to be, and it was not mishandled. And two, the harm that came on him would have occurred whether he had specifically participated in the study or not. So now we have kind of two definitions of privacy. One that's not strong enough, and one that makes it one that's so strong that really science itself could not function without it. So that leads us to differential privacy. Most basically, differential privacy is a safety against arbitrary harms. The idea is that no matter what your data is, and no matter what thing you're concerned about occurring because of the use of your data, that thing becomes almost no more likely if you allow your data to be included in the study compared to if you do not. So how does differential privacy achieve this? Well, the key idea, and this is straight from the book, is that adding or removing the data record of a single individual does not change the probability of any outcome of using the data by much, even in the worst case. no matter what records the other individuals have provided and no matter how unusual the added or removed data is. It's a promise that no outside observer can learn very much about any individual because of a person's specific data, while still allowing observers to change their beliefs about particular individuals as a result of learning general facts about the world, such that smoking and lung cancer are correlated. So, now you may be asking, what do you mean by much and almost? Well, differential privacy is granular in a way. It's based on a privacy factor. Basically, if you have a privacy factor of 2, then no outcome of using the data should be more than twice as likely as without it. Or, to be looked at another way, if an observer were to guess if a person's data was included in a data set or not, given the output using their data in the output without it, they would be no more than twice as likely to guess correctly than by randomly guessing. This is with a factor of 2. At this point, you may be thinking, well, that's cool and all, but how do you implement it? The key to differential privacy is randomness. By strategically implementing randomness into your algorithms and data collection, differential privacy can be created through essentially noise. To explain this, I'm going to use an example from the book. The example is polling the population of a city to get an average of how many people have cheated on their spouses. If you were to conduct this poll the traditional way, you would simply call as many people as possible who lived in the city and ask if they had cheated on their spouse to get a representative sample, then add up everyone who said yes, divide that by the number of people polled, and you would have your answer. However, this is nowhere close to private. We have now collected a ton of compromising information that, if it was, say, subpoenaed in a divorce filing, could cause harm to the polled, or if it was stolen, it uses blackmail. So, what should we do instead? Again, you should call up a reasonable sample of people, but then before answering you, they should flip a coin and tell us how it landed. If it was heads up, they should honestly tell if they have cheated or not. But if it was tails, they should flip us a second coin and only just tell us the result of that flip. Now, if the results are subpoenaed, they would have plausible deniability. They could just state that their first coin came up tails. Their data would still be useful, as 75% of the time we are told the truth. Either the coin lands on heads and they answer truthfully, or it lands on tails and they happen to give us the correct answer 50% of the time. The key is that while this data now has errors, we know exactly where those errors come from, and with a large enough sample, we can simply remove them. So how do we go about getting this error out of our data? Well, suppose, for example, that it happens that 1/3 of the people in the city have at some point cheated on their spouses. So now we can figure out how many do we expect to have answered yes. This is easy enough to compute, since we know that people answered truthfully 3/4 of the time. 1/3 of the people have a truthful answer of yes, and 3/4 of those will report yes, for a total of 1/4 of the population. That's 1/3 times 3/4. Additionally, 2/3 of the people in the survey have a truthful answer of no, and 1/4 of those will report yes, for a total of 2/3 times 1/4, which is a 6. In total, we expect 1/4 plus 1/6, or 5/12 of the population to report yes in this case. So, if we observe that 5/12 of our survey population have reported yes, then we can work backwards to deduce that approximately 1/3 of the people in the city have cheated on their spouses. Hopefully it's not that high. In this concept of applying randomness can be applied to more complicated algorithms. Google and Apple both have introduced differential privacy in some of their data collection that they started in 2014. Interesting, they didn't add it to their old data collection methods. They just, going forward, started adding it in 2014. And I don't know if they do it for everything. But the idea is the phones themselves locally perform these coin flips, and then they send that information to Google or Apple. So theoretically, they have no way of knowing if you're one of the ones who are lying, or one of the ones telling the truth, or one of the ones giving the results of the coin flip. Differential privacy, however, is not perfect. It's only good for protecting the secrets of individuals, not groups. An example of this is, again, given in the book. The fitness tracking app Strava allows users to upload their data from their Fitbits. Many military personnel use Fitbits. You can probably see where this is going. In November of 2017, Strava released a data visualization of the aggregate activity of all the users. It was cool. It allowed you to see in all the major cities where people go on runs most often, the most popular routes. However, when these soldiers are running on all run the same route on these secret military bases, their data ended up on Stravia's maps, revealing their locations. It wasn't showing any individual's route, but it was showing the most common route by the people in that area, which is dangerous. Another thing to keep in mind is that if a person defines harm as their data being included in a study, then their data really can't be used without violating differential privacy. For that reason, this is just my opinion, I feel that differential privacy always needs to be opt-in, and also some of those implementations by Google and Apple aren't truly differential privacy. So I hope that by watching this, you have learned something about differential privacy and how to implement it in the future, some things to look out for, and why it's important. Yeah, so thank you for watching.